Welcome to RoboLectro's Robocup journey. We are excited to share our experiences, achievements, and problems faced during the Robocup 2023 Bordeaux, France season. Before building our first prototype, we researched on all possible combinations in the evacuation zone and found out that there were more than 120 different combinations. So we decided against the idea of randomly moving in the zone and instead use either a camera or a LiDAR sensor to locate the balls and pick them up precisely. For our first prototype, we decided to use one motor on each side of the robot. But since we wanted a 4-wheel drive, we used a timing belt system to connect the front and back wheels to a single motor. After building this and testing it out, we faced quite a few problems with this mechanism. The timing belt needs to be in tension so that the teeth don't slip, but this force deformed the plastic 3D printed components, and the wheels were not in line. Also, due to the length of the motors, the width of the chassis was too large. Next, we tried to use 4 servo motors, but the RPM of these motors were very less since they had a high gear reduction, and they didn't have a continuous rotation motor encoder. Finally, we decided to use the N20 motor with gearbox and a brass coupler connected to a bearing in order to attach the motor to the wheel. We have 2 normal wheels in the front and 2 omnidirectional wheels in the back to reduce the friction while turning. Initially, we tried to use the Arduino Nano as our microcontroller, but later switched to the Teensy 4.0 as it has more number of interrupt pins, which is required for the motor encoders. We constructed the evacuation zone using wood and designed it so that the entry and exit points can be changed. This allowed us to test all the 120 possible combinations. For our next prototype, we added a few more sensors for the line follow, added more electronics like a boost converter, I2C expander, and an IMU. Since we had 2 color sensors which communicated through I2C protocol and had the same I2C address, we used an I2C expander to communicate with both the sensors simultaneously. To make sure the robot doesn't get stalled on the ramp, we use the IMU to detect when the pitch angle increases and accordingly increase the motor speed. Next, we built our final prototype. We added a ball gripper controlled by servo motors, a container, a Raspberry Pi, and a camera. Then we worked on the transfer of data between the Raspberry Pi and the Teensy microcontroller by using serial communication. The robot enters the evacuation zone by sensing the silver line. Then it slowly turns until it finds a silver ball. To detect the victims, we have used an ML algorithm which runs on the Raspberry Pi. After it finds the silver ball, it slowly moves towards it while tracking the ball. Then, using the gripper and the 3 servo motors, it picks up the silver ball and deposits it in one of the containers. So this is what the camera sees when the robot is in the evacuation zone. The camera which we used has a resolution of 720 by 1280 pixels. So after it has found a silver ball, it checks the midpoint of the bounding box of the ball and then subtracts it by the midpoint of the frame, which is 640 pixels. So the error in the position of the ball will be 640 minus X pixels. This error value is sent to the Teensy microcontroller from the Raspberry Pi through serial communication. The Teensy uses this error value and multiplies it with the KP value to give the output of the proportional controller. This output is sent to the move steering block, which makes sure that the ball is always in the center of the frame of the camera.
First, we started by capturing around 250 images using the Pi camera. Next, we used a software called Label IMG to label all the victims and safe zones present in each image. Once labeled, we split the images into 3 sets: the training dataset, the validation dataset, and the testing dataset. The training data is the data that our model is trained on. The validation dataset is used to validate the model as it undergoes training. The testing dataset is used to test the model's accuracy once the training is done. For each image, label.img creates an XML file containing information about the bounding box coordinates and class labels. We then moved on to training our model using TensorFlow Lite, and the model that we used was the SSD MobileNet version 2 FPN Lite 320.